My name is David Krause. I'm here from Nashville. I've been to a few PhreakNIC conventions in the past. I think my first one was PhreakNIC 3, so I've been around for a while. I'm going to talk about IPv6 today, what it is, why we need it, when we're really going to see it in use, and security implications of it, that kind of thing. So I studied at Vanderbilt University. I didn't finish there, but I got a lot of knowledge from there while I was there. I have certifications in PCI, which is the payment card industry. I also am a systems and network and security administrator in town. So that's kind of my background. And I've been an OpenBSD developer since 2003, David at openbsd.org. And I've been using IPv6 since the last over 2 years now. I got into it mostly because of OpenBSD. We needed to test some firewall changes that were causing problems in IPv6, that kind of thing. That's how I got started. And since then, I've been running my personal website, email, all that kind of thing on IPv6. And then just the little thing at the bottom, if you get interested in IPv6 and you start setting it up at your house, you can go and get an online certification. It's free. You just take a test, and you have to send an email via IPv6 and have a website accessible to IPv6 and a few other things that they require you to do. And then they send you a free t-shirt, so free stuff. I want to kind of dedicate this talk to a friend of mine who passed away a few years ago. He was a lead developer on IPv6 issues. He traveled around the world. He was on the engineering task force, and he wrote some of the RFCs for IPv6. He was a developer on OpenBSD, FreeBSD, NetBSD. He has some access to Darwin, which is macOS 10's code base. He was just phenomenal, and he wrote basically the book on IPv6 programming. Unfortunately, he passed away about 3 years ago. And this was a picture that I took of him. I've had a chance to meet him in person 3 times, and we corresponded via email many times than that. But this is a picture of him, and he'll be missed. Okay, IPv6, as you probably know, it's kind of complicated. I don't think it's I think it's about the same level as IPv4. It's just we're used to IPv4. We've used it for years, and this is a new thing, so you just have to get over the learning curve. Because of that, I can't dive into all the technical details today. We're going to kind of give an overview, why we need it, that kind of thing. And so I just assume that you don't have to know Linux necessarily. You could be Windows or whatever. But we need to know some firewalling experience and some TCP/IP experience, that kind of thing. I want to just do a quick show of hands in here. Who here is using IPv6 right now? And then who here is using IPv6 but they don't know they're using it? And that's probably almost everybody in the room. And as we'll see, most operating systems nowadays, most of the Linux distributions, VSDs, all like Windows 2008, Windows 7, all that kind of stuff has IPv6 turned on, and you could be attacked over it and you wouldn't even know it. So you need to at least learn about it, if nothing else. And then I kind of want to have this be open a little bit. Does anybody have some misconceptions about IPv6 or things you've heard, that kind of thing? Why should you care about IPv6? Well, the obvious one is we're running out of IPv4 addresses. There are some other benefits to it besides the shortage of addresses. That's one of the main ones. They've actually simplified some parts of the technology and complicated other parts of the technology, so there's trade-offs there. If you're an ISP or if you maybe provide services to the government because they're now requiring IPv6, you can use it as a business need and get ahead in your industry by offering IPv6 when other people aren't offering it right now, that kind of thing. So, and another reason is that people have already started deploying IPv6, and we're trying to get rid of NAT because of NAT breaking end-to-end connections. As far as the exhaustion, you probably read a lot about in the news recently. They've been talking about it more and more. Obviously, we have cell phones, we have TiVos, we have all these things like your Comcast TV box. I mean, all these new devices, stuff we haven't even thought about. Probably have IPVs in your shoes and stuff at some point. I mean, there's just all this stuff. I mean, if you just think maybe we have like 6 billion people in the world, we only have 4 billion addresses in IPv4, and obviously a lot of them aren't even used. Like each subnet obviously has lots of addresses that go unused. So we don't even have enough for one IP address per person in the world. And if you think about all the devices that we carry around, like our cell phones and everything, we might need just 10, 20. I mean, we're going to need a ton of addresses. And many of the developing countries, like in Africa and China and that kind of thing, they got kind of screwed early on in IPv4 deployment, so they are really hurting there. We've tried a number of things to help the exhaustion, but so far they've kind of delayed the time running out of addresses, but they haven't fixed the problem. Classical networks, CIDR, NAT, obviously everybody's using NAT now. They've been more restrictive about how they give out addresses on IPv4 now. It's very hard to get an IPv4 address, or a whole block of them, in other words. We did name-based virtual hosting. Before, you had to have a separate IP per website. I mean, that's been a while now that you had to do that, but that was another mitigation that was done. But the end result is we're going to have to go to IPv6 eventually. We are going to run out. This slide in here is an important slide. You're going to have to kind of understand a little bit how numbers are assigned. And IPv4 and IPv6 numbers are assigned the same way. But when you read in the news about IP addresses running out and that kind of thing, you need to know where they're running out at, what level, because once we start getting into this, we're going to run out of addresses at the top, and then they're going to slowly trickle down until we run out of addresses at the bottom. So at the very top, we have the Internet Assigned Numbers Authority. They don't give addresses to anybody directly except for the regional internet registries, and that's the, you probably heard of ARIN, RIPE, APNIC. Each part of the world has their own registry. It's basically per continent. Then you have your local internet registries, which are ISPs, universities, large businesses can go, and they go to each of the people above, to ARIN in our case, and ask for a block of IPs. And then finally you have the end users, and they go to the ISPs. Well, when you get like a router from Comcast, it comes with one IP, for example, that kind of thing. So when you start reading the news about a shortage, you need to pay attention to where the shortage is occurring, and it's going to start at the top and flow down. There are several websites online that they're doing some research into this, trying to predict when the shortages are going to occur. And these numbers are about a month old. I haven't checked since about a month. But they're saying that May of next year, the Internet Assigned Numbers Authority is going to run out, and they're going to. This is the first step, and then the first regional authority is going to run out in January of 2012. And then obviously the ISPs are still going to have IPs even at that point, but then they're going to run out after that. So it's going to slowly trickle down to us. And these are some websites you can hit up to read more about it. They have all these charts and all this predictions and everything. And we also have to kind of talk about NAT. NAT's kind of good in some ways and it's bad in other ways, but it breaks a lot of the principles that the internet was started on. Originally, every box could talk to every other system on the internet. Now, obviously, since then, we've had a lot of security problems and other things, and it's been necessary to put firewalls in the middle. You probably don't want every box to talk to every other box now. But with that said, NAT rewrites packet headers. It mucks with the internals of the headers. None of that stuff is very good. Breaks a lot of things like voice over IP, video conferencing, all sorts of tools we have now have to work around NAT. And also, if you think about it, whenever two companies merge, most of the time they're using NAT now, which means they have a non-unique address. And when they merge, the company has to figure out what to do if they have overlapping subnets inside their networks. So with IPv6, every network and every IP has a unique IP globally, so that even if two companies merge, you don't have to worry about collisions there. And then the final thing is port exhaustion, if you NAT everybody to one IP, and you maybe have like a few users that are running peer-to-peer, other things, that can suck up a ton of ports. You only got 65,000 ports available, so that's a very common problem too when you start adding too many people behind a NAT. So just in general, we want to try to get rid of NAT, and that's what IPv6 does also. Some requirements to be able to use IPv6, it's not backwards compatible, so you have to have both IPv4 and IPv6 connectivity at the same time. There are problems, I mean, for sure there's going to be systems that never get converted. They're always going to be running IPv4, and there's definitely going to be systems that start out on IPv6 only and don't go IPv4 at all. But in general, most people are going to have to run both at the same time. There's two ways to get connected on IPv6. The most common nowadays is to get a tunnel, and you basically open a tunnel out to some provider on the internet, and they tunnel all your IPv6 traffic out to them. I use tunnels. There's really not. There's a couple of different ones, Hurricane Electric and 6xs.net. I use both of those actually. When I plugged in my laptop onto the Days In network, I actually couldn't get out through my tunnel, so I'm using my cell phone for this. They only allowed port 80, I guess. I don't. It was because most of these tunnels use UDP, other kind of things that work over NAT. So, also we're going to have to upgrade routers, firewalls, other hardware. Any kind of device basically has to be taught how to understand IPv6. Now, fortunately, a lot of devices nowadays, modern devices, are coming with IPv6 support. But obviously, you have lots of legacy stuff out there that's going to take forever to get converted and upgraded. And don't forget, we're going to have our IT staff, our customer service people, tons of people are going to have to learn about IPv6 to be able to support it and implement it. And IPv6 has very long addresses, so you probably don't try to remember a 64, 128-bit number, so you're going to want to use DNS even more than you do now. This is the comparison between IPv4 and IPv6 addressing. IPv4 obviously is a 32-bit number with the 4 quads, like 192.0.2.53, and IPv6 is a 128-bit number, and it's written as hexadecimal. That's one thing you'll see about IPv6 is it's designed to use the MAC address in the address. You don't have to do that. You can do static IPs, that kind of thing, but most addressing is going to use the MAC address. And there are RFCs also to randomize your MAC address if you don't want because that's basically going to show up publicly that you have a Dell computer because that MAC address is registered to Dell or whatever. So there are RFCs to randomize the MAC address also. IPv4, you can see it has 4 billion addresses. I'm not even going to read this number off, but you can see how many addresses IPv6 has there at the bottom. Ton of addresses. And one thing you'll notice is that some people think of IPv6 as being a new protocol. Well, really, we've had it for like 15 years now. I mean, it started being developed in 92, 93. It got standardized in 95. And they started deploying it in 1999. So it's been around for a while, even though we might think of it as new. And one thing you'll see is that some features in IPv6 have already been deprecated even because it's been around for so long. I mean, all this was before the .com boom and all this, the security problems we have nowadays. So even that, it's already kind of behind the curve a little bit. Okay, this just kind of talks about how you would get allocated an IPv6 address and how big your subnet would be, that kind of thing. It works the same as IPv4. You start at the Internet Assigned Numbers Authority, and they allocate a /16 block to the regional people, and then it flows down from there. You can kind of see it up here. Each subnet in IPv4 is half of the bits in the address. So each subnet has that many addresses in one subnet. You can see that at the bottom, 18, I don't know how many billions of IPs that is there. So you already have way more in one subnet of IPv6 than you have in the whole internet of IPv4. And what you'll see also is that each customer also will get a very big subnet. So like if you go to Comcast eventually and you get an IPv6 address, you're probably going to get more than one subnet. So you're going to get tons and tons of IPs. Some advantage of the way they designed IPv6 is that you use it and manage it similar to IPv4. It's got the same concept. The ports are all the same. A lot of the stuff that we know about networking operates the same. There are differences, but in general, it's very similar. Obviously, it has a larger address space. And this is where I was talking about the MAC address. It's called auto configuration. And basically, you don't need a DHCP server. The host comes online and automatically configures its IPv6 address automatically. You don't have to have a server running to do that. In IPv4, you had to have DHCP, and some IPv4 stacks didn't even support DHCP. IPsec, a lot of people talk about how IPv6 has IPsec support. Well, that's true. It's mandatory to have support for it, but IPv4 also has optional support for it. So it's not really that much of an advantage. It's going to be there either way. QoS is kind of the same thing. We have QoS support in IPv4. It just wasn't there originally, and now it's built in. And then multicast is going to be mandatory. And what you'll see is there's no broadcast address like you have in IPv4. Instead, you have a multicast address that is used instead. And multicast is also used to do the auto configuration using the MAC address and whatnot.
Oh, I had a question about not needing DHCP. How does it do the auto configuration to figure out what subnet it's on?
Basically, your router is configured to broadcast, like it does a multicast address to the. Basically, each host has a what's called a link local address, which comes up. It doesn't have to have a router or anything. It just comes online, and automatically. So what you'll see is if you don't have IPv6 configured, but you have it enabled on your laptop, like a Mac or Windows or whatever, you'll see this link local address even though you're not using it. And it uses that to talk to the router, and the router has a list of subnets, and it can broadcast the subnets to use.
Okay, and that's auto configuration, which is kind of, in a way, a replacement for DHCP.
Yeah, kind of. And they do have DHCP also. It's called DHCP v6 because some people want to hand out, I mean, like I said, some of this was written a while back, and some people want to hand out NTP servers. Some of that stuff's not supported with the auto configuration, so then you have to have DHCP v6.
All right, thank you.
She was asking, your router knows what subnet to give, but based on where you plug in. That's correct. One thing you'll see is that it becomes very easy to renumber networks. If you want to, in IPv4, you gotta set up DHCP and all this kind of thing, and you gotta wait for the lease to expire. In IPv6, you can actually have multiple IPv6 addresses, and it's designed to be easy to renumber networks, and you just kind of plug in, and it just kind of works. Another range, and I really like this fact, is that in IPv6, the subnet size is fixed. You can't, in IPv4, you can have subnets of all different sizes. In IPv6, you have one subnet size, so it becomes very easy to, you don't have all this stuff like /15, /23s, all this stuff. You can, at the ISP level, they can aggregate multiple networks, and then you start seeing the bigger ones, but at the actual subnet level is always the same in IPv6. I think there's going to be people running IPv4 still 20 years from now. I mean, it's still going to happen. Unfortunately, we're going to have to have some translation mechanisms that it'd be kind of like NAT, but then you'll NAT from an IPv4 to an IPv6 or an IPv6 to an IPv4. I think most people are going to get converted over, but I think we're always going to have some legacy systems somewhere that are going to be IPv4. As I said before, your broadcast is now part of multicast, which makes sense. That's what multicast was designed for. Also, I talked about the routing table aggregation. It's designed to work a lot better than IPv4. And they simplified the packet header and that kind of thing with IPv6. And that's all designed because our routers are starting to get overloaded nowadays with all the different networks that are connecting. It's supposed to help our router CPU and load and everything. Unfortunately, we've run into a lot of problems trying to switch to IPv6. And you can go online and read there's all sorts of, Google has done all kinds of studies. They've secretly put in the JavaScript headers of google.com, they put in tests to see if you're using IPv6 and that kind of thing. And they've done all these studies to figure out, well, can we turn on IPv6 for google.com? And the answer is no, because there's a certain percentage of users out there that can't connect to google.com if that's turned on. And some of the issues are listed here, but there's some routers that don't understand the DNS record for IPv6. There's also firewall problems. Maybe a system has IPv6 support enabled, but it can't actually connect to the global internet. For some reason, maybe a firewall's dropping the packets or whatnot. So then all of a sudden, if we turn on IPv6 for a website, that website would be unreachable. Just lots of different problems. You have home gateways that are broken, maybe don't know what to do when they see those kind of packets. I've seen lots of issues with Java applications. If you have IPv6 enabled on a host, it can break certain things. There's a lot of problems with trying to convert. Also, if you want to take a security stance on it, I mean, you probably want to disable IPv6 if you're not using it, and then it's going to be, then later on you're going to have to turn it on once you want to use it. So that just causes delays in the deployment and everything too. Okay, so how do you get connectivity to the IPv6 internet? And there's different transition mechanisms. There's one term you want to learn that's called dual stack, and that means you have IPv4 and IPv6 connectivity at the same time. Eventually, we'll be able to see native IPv6. Unfortunately, in the US, we're kind of behind Europe and Asia. A lot of ISPs already have native IPv6 support. There's only a few places here in the US that you can actually get it, and I think for consumers, that's pretty much nobody in the US. Yeah, Comcast is doing trials, but they're very limited, and they're working on it. I mean, there's Comcast, Roadrunner, a lot of the different providers. Google has a conference every year. I think it's called IPv6 Implementers. You can search for it online, and you'll see like all these different ISPs in the U.S. that come to that conference and put their slides online. You can go read all the slides and see what their plans are. There's two kinds of tunnels, though, because most people aren't going to be able to get native, so they're going to have to go to a tunnel connection for now. And they're automatic tunnels. Like Windows 7 has a thing called Trado. You probably read about that. There's 6 to 4. There's several different kinds of tunnels that you just plug in, and your tunnel automatically comes up, and you're on IPv6. And then there's configured tunnels where you have to go out to a provider on the internet and register with an address, username, password, all that kind of stuff, and then they'll tell you how to configure the tunnel. The automatic ones are kind of problematic, and that's kind of where that previous slide with all the problems. If you have an automatic tunnel and then your router starts dropping your packets, your host thinks you're online, but you're not really, and then you start having timeouts and websites are unreachable. And also, what do we do about the hosts that can never upgrade to IPv6? And what do we do about the people who can't get an address and they have to start out with IPv6? And that's where some of these NAT type technologies are going to come into play, where you have a router and it translates from IPv4 to IPv6. In order for that to work, it has to capture DNS requests and rewrite DNS basically on the fly, and then rewrite the packets, obviously. That's kind of complicated, but unfortunately, that's something we're going to see. Right now, like I said, most modern operating systems have IPv6 support. You can see up here. So chances are you probably already have support for it in your OS. Okay, IPv6 without NAT. And basically, a lot of people think that they need to have NAT. They're like, how do I operate my network if I don't have NAT? How do I keep hosts on the internet from connecting into all my hosts that I don't want to? I mean, the answer is the firewall. NAT includes a firewall, but you can just use the firewall without the NAT. You don't have to have NAT. And so that's one thing a lot of people don't understand. You could actually just don't allow any inbound connections and only allow outbound connections, and that's the same thing as having a NAT set up. So you don't have to lose your security just because you're on IPv6. One thing we're going to see, originally IPv6, they wanted every host to be able to talk to every other host when it was designed. They wanted to try to get back to the roots of the internet, basically. Well, nowadays, with all the problems, the viruses and other things that have been going on, obviously you don't want to have end-to-end connectivity. So we're probably going to see, you're going to have a host firewall or a network firewall to keep connections from coming in that you don't want, basically. Another issue, I put this one here because of my training with PCI, the payment card industry. They actually require you to use NAT in the standard. So you have to use compensating control just to use IPv6 if you want it to. I think they're going to update. They always update the standard every few years, so they're going to take that out of there eventually and put an exception for IPv6, I'm sure. But like I said, as long as you block all inbound connections, that's basically the same as having a NAT. Also, PCI requires a DMZ and that kind of thing. So your network's going to look very similar. Even if you have a globally routable address inside, you're still going to have that DMZ and the firewall rules in place that block it. Like I said, we're going to have a lot of misconfigurations because people don't understand. They might not have a firewall turned on. These automatic tunnels are kind of a problem because they're tunneling out of your network and you may not realize it. They're kind of hard to block because they're designed to traverse NAT and that kind of thing. Also, like I said, if you have IPv6 support in your OS but you're not using it, that doesn't mean that you're not reachable on the local LAN via IPv6. And so you can port scan people, you could connect to them if they have IPv6 enabled service such as SSH or remote desktop or whatever. So if you have a Linux box, you can do this ping6 command. It's a little bit different syntax on BSD, and then on Windows you have to slightly different syntax also. But you basically can issue this command. I checked the network here earlier, and I didn't see anybody on that had a v6 support, so I'm not sure why that was. Normally you go on any network that has lots of hosts, and you'll see all these hosts that are responding on the link local address, which is the and you ping that multicast, and you'll see all these hosts on there. So you guys could try that in the root wars and stuff. Also, we're going to have a lot of new vulnerabilities that are going to pop up because both the design itself, there was a vulnerability in the design that was found a couple of years ago with the routing headers, and everybody had to patch. We're also going to have new vulnerabilities in the implementation because it's all new code. It's not been tested. Just to give you an example, a few years ago, there was a bug in OpenBSD that if you pinged a host, every ICMP packet you sent, there was a memory leak. It wasn't a vulnerability as far as remote exploit or anything. It was just basically it would be a denial of service if you'd done it enough. But it was basically every packet that you sent on IPv6 ICMP got leaked, and eventually you could take up all the memory. Now, nobody noticed that because we weren't using it that heavily. So what if you lost a few K of memory and you don't notice it? So we're going to see a lot of those kind of problems too. And then also things like DDoS attacks. They're already figuring out new ways to basically break IPv6 because some of these new features and whatnot. There's a way, because the address space is so big, you can actually start a port, not a port scan, an IP scan, and you'll start filling up the route. It's almost like an ARP cache, but in this case it's neighbor discovery cache, and you'll start filling that up. And if you fill that up on the router, it causes basically a DDoS basically. So, I mean, there's going to be a lot of problems, and we'll have to sort through all these basically. One thing that I put here is that I'm using Google Docs for this presentation, and the reason I did that was because Google has a service where you can connect to them over IPv6. It's not their normal DNS. You have to connect to a special DNS server through one of your tunnels, and then you can connect to Google over IPv6. So I went and did my presentation over IPv6, and right now I'm running a tunnel through my cell phone, and I'm connected to Google over IPv6. Okay, I was probably going to have let's say we got 5 minutes here for more questions, and I could drop to the command line and show some examples, whatever you guys want to see.